Now in this video, we will going to take up one more problem. The problem number 20 on the draw the SFD and BMD for the beam shown in figure and locate the point of inflection, if any. So it's a overhang beam on the one side. So we have a support between A and D, but it overhangs by some distance in the point E by 2.5 meters. It's a overhanging beam. So if you read this problem, you can see between A and B, you have a 10 kilonewton per meter for a span of 5 meters. Then at the point B, you have 80 kilonewton also acting on the point load. And at the point C, we have 80 kilonewton acting at the point C, which is at a distance of 7.5 meters from A. And also at the point D, you have a support reaction at the point D. And also you have an uniformly distributed load of 16 kilonewton per meter till to the point E, which is at a distance of 2.5 meters from D. So now we have the vertical reactions at A and D. So that is RAV and RDV we need to find out. So to do that, so first we are going to take the moments, so first the support reaction. To do that, taking the moment about the point A. So that means again you are going to have the clockwise will be equal to anti-clockwise. So here RDV into 12.5. RDV into 12.5 will be equal to, so you can see, first we will go to take 16 kilonewton per meter for a distance of 2.5 meters. So W into X, so W into X by 2. So that means 16 into 2.5 into, open the bracket, 2.5 by 2 plus 5, 10, 12.5. So that is equal 16 into 2.5 into, open the bracket, 2.5 by 2 plus 12.5 and close the bracket. Then plus 80 into 7.5, 80 into 7.5 plus 80 into 5 plus 80 into 5 plus 10 into 5 into 5 by 2. So 10 into 5 into 5 by 2. So that's what. Once you get this, so on simplification, you will going to get RDV will be equal to 134 kilonewton. Therefore, the reactions at the support, vertical reaction at the support D will be equal to 134 kilonewton. Also what we know, the sum of the vertical reaction acting upwards will be equal to sum of the vertical reaction acting downwards. So also RAV plus RDV will be equal to 10 into 5 plus 80 plus 80 plus 16 into 2.5. So that means 10 into 5 plus 80 plus 80 plus 16 into 2.5. So what is RAV now? So 50 plus 160, 210 plus 250 minus 134, because taking the value of RDV, which was 134, substitute that and take it to the right hand side. Then RAV will be equal to 250 minus 134 will give you 116 kilonewton. So the reaction, vertical reaction at the support A will also be equal to 116 kilonewton. Now once you find out the vertical reaction, so then now the beam is in equilibrium condition, because the sum of the vertical loads which is acting upwards will be equal to the sum of the vertical loads acting downwards. So now the beam is in equilibrium condition. Now therefore, once you get this, now we will go to start with the individual span. So first we are considering between A and B. So we have vertical reaction at this point A, which is RAV is equal to 116 kilonewton. And then you have a 10 kilonewton per meter for a span of 5 meters till to the point B. So now initially we will not consider the 80 kilonewton now. So what will going to be the shear force at the point A? The SF at A will be equal to plus 116 kilonewton. Then SF at the point B will be equal to plus 116 minus 10 into 5. So that will be equal to 66 kilonewton. So at this point, shear force at the point B will be equal to 66 kilonewton. SF at A will be equal to 116 kilonewton. So it drops 116 to 66 by a linear line, because it's by the straight line, because it's a UDL. So therefore, SF will going to vary from 116 kilonewton to 66 kilonewton according to the equation of straight line. due to UDL. Now we will going to take the bending moment at the point A. So BM at A will be equal to 0. So BM at the point B will be equal to plus 116 into 5 because it will going to sags at the point B as the vertical reaction making the beam to move in the upward direction. So the beam will also tends to deflect in the upward direction. So therefore, by convention, it is positive. So 116 into 5 minus 10 into 5 into 5 by 2. So on simplification, you will going to get it as plus 455 kilonewton meter. So we will going to plot that. So at this point 0, bending moment at the point A is 0 and the bending moment at the point B is 455 kilonewton meter. So once you get this, so we can join between these two because there is no shear force which is crossing the XY line, crossing the 0 line. So plus 455 kilonewton meter, since it is W into X by 2, since it is a UDL, so therefore the bending moment, in bending moment diagram, the bending moment changes from 0 to 455 kilonewton by means of a parabolic curve. So once you do that, now we are going to apply the load at the point B, which is 80 kilonewton, and then extend that beam to tilt to the point C without considering the point load at 80 kilonewton on C. So we will not consider the 80 kilonewton point load, but we are going to consider only the segment at this point C now. So what will going to be the shear force at the point B now? Shear force at the point B will be equal to plus 116 minus 10 into 5 minus 80. So on simplification, you will going to get it as minus 14 kilonewton. So then, so what happens? Bending moment. So here, the bending moment drops down from plus 66 kilonewton to the minus sign, which is minus 14 kilonewton, because due to the point load at the point B. So between B and C, SF remains. So then what happens? Now we need to consider, so till 14 kilonewton you will get minus 14 kilonewton. Between B and C, as there is no other load is acting on the beam, so SF remains constant. So from 14 kilonewton at the point B, minus 14 kilonewton at the point C also, because we are not considering the point load. Now we are going to consider the point load, see what happens. Once you consider the bending moment at the point C now, first we have find out the shear force at C. Now we will going to consider the bending moment at the point C now. So bending moment at the point C will be equal to plus 116 into 7.5 minus 10 into 5 into 5 by 2 plus 2.5 minus 80 into 2.5. So on simplification, you will going to get it as plus 420 kilonewton meter. So once you plot that, so you can see from 455 kilonewton meter, the beam bends, the bending moment diagram reduces from 455 kilonewton meter to 420 kilonewton meter at the point C. But when you are considering the point load now at the point C now, when you are considering the point load at the point C, which is 80 kilonewton acting downwards, and also from C to D till here, so where at the point D you have a vertical reaction, which is RdV is equal to 134 kilonewton. So once you apply that, see what happens. Shear force at the point C will be equal to minus 14 minus 80, it becomes minus 94 kilonewton. So that is what? Between C and D, as there is no other load is acting on the beam, therefore it will be remains constant at minus 94 kilonewton. So at minus 94 kilonewton between C and D. But because due to the point load, SF drops from minus 14 to minus 94 kilonewton. So what will going to be the bending moment at the point D now? So bending moment at the point D will be equal to 116 into 12.5 minus 10 into 5 by 2 plus 7.5 minus 10 into 5 into open the bracket 5 by 2 plus 7.5. So again minus 80 into 7.5 minus 80 into 5 minus 80 into 7.5 minus 80 into 5, which will be equal to, on simplification, you will going to get it as minus 50 kilonewton meter. So now what happens? So once you come to this point, so from the bending moment point C, because due to because at the point D, it drops down from plus 420 kilonewton meter to minus 50 kilonewton meter at this point C, at the point D. So now Once you get this, now we will going to consider the total value of the shear force at the point D, which is minus 94 minus 16 into 2.5 minus 16 at the point D when we are considering here. So what happens? We have the vertical reaction at the point D, which we have considered now. So once it is minus 94, since it is going to, it is the vertical reaction acting upwards, so it becomes positive as by sign convention. So minus 94 plus 134 kilonewton, it becomes plus 40 kilonewton. So SF at the point E will be equal to plus 40 minus 16 into 2.5, which becomes equal to 0. So what happens at the point D, which was 94 kilonewton, minus 94 kilonewton, when you're considering the load at the point D, which is acting upwards of 134, so minus 94 plus 134 will be equal to plus 40 kilonewton. So SF rises from minus 94 to positive 40 kilonewton because due to the point load at the point D. Now, what will going to be the bending moment at the point E now? So the bending moment at the point E will be equal to, so 116 into 15 minus 10 into 5 into 5 by 2 plus 2.5, 7.5, 10. So 10 into 5 into 5 by 2 plus 10. Then again, minus 80 into 7.5 plus 2.5, it becomes 10. Minus 80 into 10. Then minus 80 into 7.5, minus 80 into 7.5, then plus 134 into 2.5 as it is going upwards. So it becomes sagging. Then minus 16 into 2.5 into 2.5 by 2 will be equal to 0. So then what happens we're going to see. So at that point, the bending moment at the point E will be equal to 0. Now, as the bending moment from minus 50 kilonewton meter, it reaches to 0 at this point. Since it is a uniformly distributed load, so you are going to get the power of x is 2 because W into x by 2. So it will be x squared by 2 since the power of x is 2. Therefore, it follows or it draws a curve. So from minus 50 kilonewton meter to 0, we are joining by means of a smooth curve, which will going to be a parabolic curve. Now, once you see this, so we need to find out what will going to be the maximum bending moment. So the maximum bending moment will going to occur where the SF changes its sign. So the SF changes its sign at the point B and also at the point D. So we can see, so the maximum bending moment will occur at a point where SF changes its sign. SF changes its sign at B and D. Hence, the maximum bending moment will be at the point B and D. So once you are at the point B, you are going to get the maximum bending moment as positive bending moment, which is plus 455 kilonewton meter, positive bending moment at the point B. And then the maximum negative bending moment is at the point D, which will going to be minus 50 kilonewton meter. Now, once you get this, as the bending moment changes its sign from the positive to negative at the point F, so that is what we call it as the point of contraflexion. So it is the point where the bending moment changes its sign. Let F be the point at a distance of x meters from E. So where the bending moment changes its sign. So first, what will going to be the bending moment at the point F now? BM at F will going to be 0. So when you are considering the section, see what happens. So that will be minus 6 into 2.5. So minus 6 into 2.5. So here, once you get this, so we will going to get from minus, it is 16 into 2.5. So minus 16 into 2.5. So that means it will going to be the total load. So total load is minus into 16 into 2.5, then into, since the section is at this point, so the total distance is x. So it will be x minus 2.5 by 2. So x minus 2.5 by 2. That is because since it is a UDL, the load which will going to be at the center. So W into x by 2. So that is 16 into 2.5 into 2.5 by 2, which is at this point. So the total distance is x minus 2.5 by 2 will going to give you this distance. So from you are considering the section at this point, this distance will be x minus 2.5 by 2. Since it is the UDL, we have 16 kilonewton per meter. So minus 16 into 2.5. So it should be minus 16. It is instead of 6, it should be minus 16 into 2.5. Then you have plus. So what will going to be that distance? So because the load is acting upwards, so it becomes sagging. So naturally it becomes positive. The beam will going to becomes positive. So that is plus 134 into total distance is x minus 2.5 will going to give the distance between x to the point D will be x minus 2.5. So on simplification, you can see minus 40 into x plus 50 plus 134 into x minus 335 will be equal to 0. So then we will go to guess 94 into x will be equal to 285. Therefore, x will be equal to 3.032 meters from the free end E. So therefore, the point of contraflexure is at 3.032 meters from E. So this is how you will be able to analyze and solve this particular problem. You can see here the x is 3.032 meters from E, and we have the positive bending moment is at the point B, maximum positive bending moment, which is 455 kilonewton meter, and the maximum negative bending moment is at the point D, which will be 50 kilonewton meter, minus 50 kilonewton meter. And the point of contraflexure is at a distance of 3.032 meters from E. This is how you will be able to analyze and solve this problem. Thank you.